All right. The thing, hold on, that was a terrible clap. All right. The thing has been hit. The thing says we're live. All right. I know we're doing a little bit of a different thing here. This isn't the standard thing. I know. I'm not even wearing a yellow shirt. I know. Informalities aside, well, why are we doing this? One, it totally helps the algorithm. Why? Because that's what you're supposed to do. And I should probably actually finally get watch time up to actually get monetization. Why? Because I would like to keep doing this, but you, you can only you can only fund something for so long. I'm sorry, unless there's any very wealthy patrons out there that would like to help fund the Physics Monastery's research. Feel free to reach out and or check out the Patreon if you want to donate a couple of bucks. It's okay. It's okay. So, what are we doing up today? What are we actually planning on doing? All right. So, this was going to be a little bit more of an interactive. I know I've been more reclusive as a physics monk, kind of just peering into questions, trying to find plausible answers, seeing if we cannot actually, I don't know, maybe verify the standard model. Basically, maybe not just completely cast aside, like, I don't know, millennia of like humans just working hard to get us to the point now where we have measurements to like 14 significant digits, maybe 16 if you do centimeters or something like that, depending upon one's perspective. I could be wrong. I'm pretty sure it's 14. Now, I'm very biased on that because, well, we have certain claims. And when you're looking at constants of nature and you see things that they seem to line up really well for about the first seven-ish significant digits. Then after that, what do we need? We need quantum mechanics. Why? Because everything is quantum mechanical, or at least according to the modern interpretation of quantum theory. Now, I'm not saying that's not the case. I think there's a lot of stuff that we don't understand what's going on, but we're trying to be less wrong because, well, we're perfectly imperfect creatures. And if one is going to try to be more perfect, well, hey, you got to start somewhere. So the whole plan of this is we're going to talk about some things we've talked about, some sciencey stuff and things. For our friends in the chat, feel free to ask away. I understand there's nowhere in the algorithm that says I should actually be on right now. It's fine. It's fine. For those temporally in the future and or joining us right now, feel free to ask away. But all right, my monastery life. Yeah. Very clickbaity. It sounded kind of cool to me. All right. Why do I say that? Because that is technically an accurate statement. Why? I am spending time at the Physics Monastery as a physics monk. Why? To figure out what's going on. All right. Let's do a real brief overview about how the heck we got here. Okay. Here's for like the sappy little personal story bit. Don't worry, it'll only be like a minute. Okay. So after getting onto the internet, because I got tired of yelling at the TV like a lot of other folks, I started interacting with different communities, started going on different lives. Oh my God, I can interact with other people, talk about different things. And then I'm like, okay, can we unite the world? Can we get over this hatred without a common enemy? I would reach out to people from over kind of more in these extremes. Some people would say, and then some of these extremes. And when you talk to people and you don't start off with you're evil, terrible, no good, and bad. When one does not start off that way and maybe like, hello, man, hello, sir. I don't know. Treats most folks just want to live a good life and be left alone. But you look at the incentive structure. What do we incentivize the people to be? Dicks. Now, I am a dick, so I believe I'm allowed to say that. It's my middle name. Like literally, I'm son of a dick. But short for Richard. I don't know. Hey, Dick Grayson is a thing. I'm just saying, Batman. It's in canon. Okay. Bloviating aside, I got sick and tired. Long story short, I found out a lot of people just don't like each other and they were looking for reasons. And it came down to more often, I like to admit, I don't like them. Now, that's an honest answer. I might not think it's a good answer, but it was an honest answer. So at that point, I realized wait a second. There's a solution to this. A lot of people are being highly offended on the internet. How can we come to some accord? How do we know that people are saying what they believe? Well, since everybody on the internet would never lie about anything or do anything for clout or clicks or anything like that, it was very simple. There's a lot of brave culture warriors out there. And as I've seen, they've labeled them as evil. Who are them? Everyone who are not us. Okay. Insert categories, group, subgroup here, yada, yada. Okay. Well, the simple solution would just legalize dueling. And then I started asking people about it. And it got far more support than I would expect. And then I realized at that point, it's like, okay, it could be the dude that helps promote the legalization of consensual murder. You play that, it doesn't sound good. And I happened to come across science. Science was always my safe space. I love National Geographic when it was National Geographic and they would teach you stuff and things. And as a scaly, did we need a special on dragons? I'm sure it was amazing. Actually, I think that actually has the actual issue where they went through it. Hey, it's fun to play, especially on the internet. But ultimately, I started going back into science, paying attention to different lectures during the pandemic and everything. Because all right, people were listening, and that was the time I went back to work because I had lost my other job and I needed money. So I was working in a warehouse, lifting things up, putting them down, and listening to a lot of science podcasts, like a lot of people are. And so I'm getting to you in the second chat. I'm sorry. Let me finish my bloviating. Give me one more minute. Okay. So what ended up happening is I got into it. I'm going to work one day. All of a sudden, I hear new on G2, new physics, all this jazz. It's like I'm listening to the scientist on. He's like, "This is our Mars rover moment." Oh my god! It's like not like the first time where we kind of crash landed, but maybe the second. It's all right. This is why units are appropriate. It's not like we did the calculations in feet and programmed it in meters. It's that was a Ron Williams joke. God rest his soul. But ultimately, I'm like, all right, this is a big deal. And I'm like, all right, that's cool. That's cool. But nobody knows why this happened. Now, I ain't a genius. I ain't the brightest bulb of the bunch. I may be the luckiest son of the gun in the world because that was on April 7th, 2021. On April 6th of 2021, I was going out for a run and I had I had followed that, and I just opened up Twitter, the dumpster fire that it is, and every once in a while there's a gem there, and all of a sudden that had posted a video. I'm like, it's happening. All right, click on it, listening to it. He's talking about all these things. I'm like, I don't know really what he means. Talking about some things, big claims. I'm like, well, half of the stuff this guy's claiming is true. This would be revolutionary. Did it with a great assault. The next day, I had those observations. Okay, so we have the Fermi Lab observations. So again, I use Twitter, the dumpster fire it is. I asked that. I'm like, I don't know. Did you cover this? Does this help your model? He responds with a yes. I go home from work, go onto Lab's website. I go onto the website, look at the numbers. I have no idea what they mean. To be fair, I still don't even necessarily know what a mu G2 is. Okay, it's supposed to go about 2 times, and it's supposed to be particularly two magnetic precession, but it lines up. Okay. Um, just look at the numbers. Go back to the video that had premiered the night before. Look at the numbers, and I'm like, dude, man, nailed it. Predicted the mu G2 results. How did he do that? Interviewed him a couple of times, came out here a few times, saw enough evidence. Because my dad, God rest his soul, and I'm finishing up right now, guys. He told me to follow the evidence. I saw enough evidence, and I'm like, all right, this is something worth spending some time looking into. I also have to, my dad passed away. He had left some money that I'm like, okay, I can spend about a year or two, maybe take some time off from my job. You can only do it so long. Hence why we're doing this to see if we can get some time, some hours, and maybe some funding at some point out there. But we'll see. Okay, so we have some people. Let's see, what do we got? Oh, we got Tally and we got Quantastic. What's going on, my friends? Are there any questions? Anything that's going on? I know I've had Kali on before. He's always a blast to have on. Very I like the balance of You got science, you got some woo, and to be fair, there were some science papers before that were written, and you're kind of like, it's almost very whimsical. It flows. And personally, I kind of view it as an art. Why? Well, why can't science be pretty? Maybe we can notate things because okay, well, was the Einstein field? Okay, look, we got this. Oh, G mu nu yada yada yada. Okay, we have that stuff. Fantastic, very beautiful. Now, if you actually go to compute some of this stuff, and I might be confusing this with a completely different metric tensor indice, it's like, all right, we got like 10 by 10 indices. It's like we compactified it into this term. Cool, cool. I mean, we can do this stuff. And now that might be a lot of work. And I think Jonathan Garage, shout out to Jonathan. He's worked on, oh, I need to reask Jonathan again. God, it's been so long. He's created something called Gravitas, which I believe the code should be on GitHub. God, probably should have. Somebody reminds me. I'll put it in after if I can remember. But his Gravitas software to help shortcut that. He's like, all right, you can still, if you still want to be very, very as accurate as possible, you can do all this stuff, or you can input your generalized parameters, and it's going to give you a really good approximation. Okay, maybe you can get more of a feel for what's going on. That's where computation and modern computers can really come in and help make a difference. So, ah, breaking each constant down. Okay. So that's a great point, Quadtastic. Let's do that. This is something that we were talking about a little earlier about different ways we can kind of actually go through. All right. So what is a constant of nature? Constant is something that more or less, God, it's a terrible name. Because even the fine structure constant, it's like, well, it depends on the temperature. So often when we get to extremals, things start to become a little wonky. And that's where field theory and stuff come in. All right, at least to my knowledge. Again, I'm not a traditionally trained physicist. I'm doing the internet that somehow ended up with the title of physics monk. Okay, so at least within the actual, I know I'm putting the cap back on the marker. We're going to hold on for just one moment. So the actual constants in nature, they are, oh, they are relationships. They are relationships because basically, to my knowledge, everything that we have is this compared to that. Because, all right, we assume we're perfectly still. Are we really perfectly still? I'm pretty sure the Earth is rotating. And then we're kind of like going through space. And then we kind of got like, we're kind of going around the Milky Way somehow. And then we're just kind of like going through, Milky Way's going through space. Where are we heading to? I don't know, the Great Attractor, Laniakea is something, something. We think this is what's going on. Is there true stillness? My claim is there would be yes. Maybe at a single point, but probably. Everything else might seem in motion. Now, that's extraordinarily speculative, so I can't really prove that. I could lay out some evidence if you would. So, all right. So, as far as the constants, it's very interesting because like we have a poster of constants. So let me just walk over and see it. Why? Because we're here. All right. So note a lot of this is being updated because as we continue to get better, we're looking for better and better grouping and everything. Okay. So we get our poster over here. Let me adjust this to gamma. All right. All right. Now is this coming through as okay? Yeah, no, it actually does come through. Okay. So we got like starting off, we got H bar. What are these guys made up of? All right. We have dimensionally different constants on the poster, and we're going through them. Okay. So you got, I'm sorry, H bar, you got two. Actually, this is easier. I actually have it on the computer itself. I know, I know. I figured it'd be quick, and then I realized I couldn't actually hold things still. So that's why I use StreamYard so I could do this. Yeah. All right. So I'll bring up a poster. All right. Updated poster. Uh, chemistry, because we have larger stuff on there. Okay. right. Go over there. Is that cream? And we're gonna go over this guy. All right. What we got over here? I'm big in it. Okay. So basically, what we were seeing right here, this should be a more updated version. But all right. So these are dimensional constants because the core of this comes from what was formerly known as the hyperbolic vortex equation, now known as the hyperbolic partition equation. It's the thing that I normally wear with a shirt. It's got the 1 over x plus x cubed divided by 2 pi set equal to I raised to the I, all of that raised to the negative pi over 2 minus out the Planck mass. Gap is the claim. All right. It gets you to the fine structure constant to all known digits. Okay. And then we believe we can have, since it's a geometric argument, we can have as many digits as we would like. Okay. Once we get that, we can start inputting them into our equations. Now for this is the h bar. So what is this? We got length squared. So that's area. So we got area, and then we got mass. So I like to view it as mass area. Why? I'm a masshole. Massachusetts born and raised. Now it's mass area, and then that's per unit of time. So it's a mass area rate. So it's like a massive area per unit of time. Okay, that's our, it's considered the unit of action. That's how I conceptualize it. Okay, so those dimensions hold for, we got h bar to like 10 digits now. We had 12, and it was kind of large error in the last two. So they defined it in like 2019 to 10 significant digits. So I believe this gets about, I think, 6 or 7 digits for the Planck units, because normally we only have the Planck units to about 5 significant digits. There's an interesting thing going on with the Planck charts. There may be reasons for that. We do have deviation from what a lot of folks, even the good folks at Wolfram, think. There are reasons for that. We'll get into them at another point. But these things, the other point is, aside from something dimensionless like the fine structure constant, if you could have more significant digits and have a reason for why it would be those significant digits, okay, perhaps we include or increase our accuracy. What if we could do the same thing with the 5 Planck constants? Now I say 5, there's all different type. Okay, let's go back to the board for a moment, shall we? All right, here's what we're going to do. So when you hear Planck's constant, normally people are talking about like h bar with a 2 pi on it, basically the cycle, the full cycle, because that's how it was originally derived. And we have h bar as a unit of action. Okay. Now, that's what you hear, but then you also have things such as the Planck time, the Planck length, the Planck charge, the Planck mass, the Planck temperature. Now, I'm giving those particular 5 because here's something else that appears to be true that I have not heard from anyone else other than Thad before. It's for all the dimensional constants that we have that was on that poster and that other poster that we're going through right now. You only need 5 dimensions of measure to create all the constants of nature, at least those 288 that we have there. And those are the units of time, the unit of space, which we express as length. And then if you had length squared, it's area. You have length cubed, that's a volume. Groovy. And we got charge. Yes, we could some charge up into that expression. There's different expressions of charges, but this is very interesting. Charge, we got mass, we got temperature. Yep, my entropy fans are in the house. Whoop, whoop. Yes, yes. Shameless plug. Shout out to Jen from the Church of Entropy. I'm going to spell temperature. Or I spelled that wrong. Always my worst subject. All right. We have these 5-dimensional ingredients. So I like to think of this as our stuff. Uh, we got dimensional ingredients. So ingredients. Okay. So we got our dimensional stuff. Okay. What is that dimensional stuff doing? I believe that dimensional stuff is doing different geometric things. Okay. Geometric. There we go. Something like that. Oh, it kind of looks like a sigh. But okay. So the claim is, I know, very, very how posh of me. We got stuff, and then we got to figure out the things that it's doing. Okay. This is how I compartmentalize in my mind when I'm watching people going over lectures. I'm talking about all these different, okay, they got this group symmetry, and I'm a complete noob. I'm like, I don't know what they're saying, but let me just chunk it in my mind. All right. So we got some stuff, and then it's doing some geometric things, some actions, if you would. When do we have instances like that? I don't know. Magnetic constant has 4 pi in the center. Why? I don't know, because it seems to affect a spherical area. That would probably be a good intuition. Or Planck's constant rather than h bar. It's got a circle in it. So it's like cycling or something. Maybe we can gain some intuition. Maybe we could do a similar thing if we're trying to parse through the constants of nature. What might these things be? Geometric actions. Oh, you got I. You've got our yes, our lemniscate. Yes, our lemniscate. It just happens to be a figure eight, aka an infinity symbol. Again, simple, different things. We got our pups, universal parabolic constants, because it's basically like pi for parabolas. Do I still need to look it up what it is? Yes, I do, because I have not committed to memory. Because, well, maybe I don't have enough computational stuff up there. And Math World and Eric Weisstein has done quite a good job at documenting that stuff. I think Math World ended up taking a lot of his stuff and playing around with it too. Okay, let's see. We got some more chess going on here. All right. I'm looking. Recently, yeah. All right. Kali Singh. I'm seeing it was derived from EO and U. Oh yeah, E naught and yeah, the electric constant and the magnetic constant. It's like 1 over the square root of E naught and mu naught. Is that how they do it? The magnetic constant, I believe that's what we have there. So that's the molecules mean. Okay. All right. Cool. So we've got some stuff doing some things. Okay. Let's go back to our poster. So what is the whole claim here? Okay. I can stand up. Yes. Oh God. All right. Let's just do this. And full screen. Okay. All right. LH bar, the elementary unit of action. What we got? All right. So we got mass, area, rate in there. Okay. And why do we have a separate piece over here? What's going on? Okay. So that's where the very interesting thing happens, because the Planck constants, except for charge, again, I full disclosure happen to have a different view about what the Planck charge may be, is the other ones we have to approximately 5 significant digits. Now you're like, oh, okay, well, we got to figure out things. Now, some of the things to remember is, well, the the speed of light we have measured, it's the two-way. We measure the two-way speed of light, but we have confidence in that to 9 significant digits. H bar, where we're just taking a look at, We had confidence to 10 significant digits. We had 12, but the error was kind of large. So they lopped it off and defined it at 10 significant digits. Okay. Yes, as I start stuttering and rambling. But why is it that if we know the speed of light to 9 significant digits, h bar to 10 significant digits, that we only know like the Planck length, L sub p, and the Planck time to 5 significant digits? Because c, as we understand it, is Planck length divided by the Planck time. That's what c is supposed to equal, right? That's a terrible question mark. There we go. Why does it? Wait a second. If but we got this to 9 significant digits. We got that to 9. Okay, but there could be some variation in there. That's very fair. But if we got h bar, pardon? Oh, ramble too much. H bar, well, that's just mass area rate. So that's Planck mass. Boom. Planck length squared over Planck time, because we were just looking at that. All right. Now we got this 10 significant digits. All right. These are different combinations, but I'm like, why do we only know those to 5? Of like all these hundreds and hundreds of different dimensional measurements, we couldn't get 7 or 6. 6. Maybe there's something interesting going on at a particular point, because 5 only really means that maybe something weird is going on about 7, because you need like an additional 2 digits to gain additional confidence in what the previous digit before then is. Something like that. I don't know. I'm not a super arithmetic person, but that seems to kind of make sense. Okay. Why did I go through all that ramble jamble? All right, so we can get back to our poster friend here. And because of the very interesting thing that happens at about 7 significant digits. So Todd was like, are there any constants of nature that happen to have around the magnitude of, let's say, the 7 significant digit, or about 10 to the -7? Coincidentally, this box right here, which, okay, I know I'm jumping back and forth. The box right there, this whole little box thingy, and I know there are different folks that use those boxes for different things, but within this notation, this is equal to, again, the Planck mass times the Planck length all over the Planck charge squared, Q sub p. And that is approximately 10 to the -7. Okay. Very interesting. That happens. It's actually like 9.999929999 yada 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 times 10 to the -8. It's pretty close. It's pretty close, I claim. Okay. Ultimately, that's shorthand for things like our a little friend like for H bar we're going over. It doesn't affect it. For some of the things where we got like 12, 13, 14 significant digits, a tiny little bit of makes a big difference. And fortunately, the more significant digits we've gotten, and the more we continue to hone, basically, mostly that grinding it out, is we're getting closer and closer to what seems to be an emerging pattern. And things have cleaned up for those of us that have been around for a while, from the original poster, where they had like, I don't know, like 40 or 50 things on it. And now it's like, all right, I got like 300 some odd data points going through. And it's like, all right, so what might be going on. I forgot to notate this, but those five-dimensional ingredients, the other part is we have claimed closed forms for them. Okay, so I can at least do this. We'll do a little walkover because these have not changed. And again, could be wrong, and there are other answers that one could actually go with. Um, I'm always happy when the goat ratio, the tether length of a goat pops up. But all right. So basically, yes, it's an early poster, but all right. So this first little thingy, that little pi sine h thing right there. All right, the claim is that's the closed form for the Planck time. And I'm realizing as I'm going over that it's probably going to terrify people away just because the first time I saw, I'm like, I have no idea what any of this stuff is. It's probably easier. Just let me open up a tab in Wolfram Alpha because I think it's my current default Wolfram thing that pops up here. Let's see. Am I Wolfram? Oh, what do you know? Okay. Yes. Terrifying thing as it is. Okay, so let's share this dude here. Okay, what we got here? All right, that's what I was showing you here in the way you can type it in. All right, so what's the whole dang claim? Whole dang claim is, all right, pi, something related to a circle. Maybe there's some curvature. All right. Hyperbolic sine squared. All right. We're doing some hyperbolic stuff squared. All right. One half. All right. It's literally breaking apart or something right there. All right. And that's all squared. Okay. The long story short, you don't have to believe any of this, but it's the methodology that I'm trying to communicate. Uh, it's that if we have a closed form that we could argue for and about a dimensional constant, if we had the ability to find something, we could have additional significant digits. So rather than having to look at all these different things, we'd literally have our dimensional scalars, if you would. I'm allowed to say scalar as long as there's not a vector involved. I looked that up. Sir, the mathematician or physicist is going to be like, you're wrong. You're wrong. Please let me know why I'm wrong. Um, but okay, the methodology is how we're going to find these, and that's why I still need to release the video. But I claim logs are useful. Why? This whole method in order to get this thingy here. Let's go over to Codata. Should be back up. I was down the other day. I think they were doing an update. Okay, so let's just do this. Go here. Okay, so let's look up Planck time. Planck time here. All right, we got these digits. All right. The whole claim is, and again, this could be completely wrong, and we got some explaining to do, but each of these things has an exponential power. Even if it doesn't have an exponential power, it would technically be one. No? But the claim is each of these different dimensional constants has an action. And at least for these Planck values, they're made up of those magnitudes. Those 44, if we take the absolute value magnitudes, okay. We're going to set the equation equal to that. Now, I understand that's a completely crazy thing, but let's just grab these numbers right here. Go back to our friend Wolfram Alpha. Okay. And here we go. Okay, so what we're going to do is add a 44 magnitude. I'm going to set it equal to 44. I'll do it this way. Okay. Now, the claim is logs are useful. Why do I say this? Because we're going to use E. We're going to raise it to that numerical string of digits that we had there. Gotta make sure we don't have them multiply. I'm going to put that in there. And again, we have this all at the 44. And we're going to solve for X. It's a crazy thing to do, unless it seems to work. Okay, it gives us a solution here. I have no idea what that means. Luckily, Wolfram Alpha might give me some suggestions. Oh, wait, what's this? Ah. Oh, wait, hold on. I didn't. Sorry, I didn't click on it. I forgot it was over. Okay. Oh, wait a second. This friend looks very familiar. That's how we got that. Basically, the claim is they are logarithmically based closed geometric actions for the Planck time, the Planck length, the Planck charge, the Planck temperature, and the Planck mass. When those five-dimensional ingredients combined with only four dimensions ever being expressed at once, not all five, which is very interesting, we get the constants of nature as we know them. Now, might there be different? Is it directly from there, or could it be of expressions of expressions of expressions? I need to learn more math because I feel like that would give us a little bit more. Hey, Hex, good to see you. Any new insights on the fine structure constant? Sure, let's do that right now. Okay. See, I feel like a base model LLM. I'm slowly learning. You just need to prompt me correctly. Okay. So anything new on the fine structure constant? Okay. Let's do this portion of the board because it's free. All right. Our standard hyperbolic, what are we calling it? Hyperbolic partition equation, aka hyperbolic vortex. So, all right. Hyperbolic. I'm gonna get a new marker. Partition. Oh god. Good thing I can't even spell that word. Uh, 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 is our standard blah 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 1 over x plus x plus x cubed over 2 pi, and then we set that expression equal to do I to the j is better because we're displaying orthogonality within dimensions because it's easier to just plug in the Wolfram alpha as I to the I, but it's I to the j. Thank you, Casey, for pointing that out. Uh, and then that's raised to negative pi over 2. And then we subtract out Planck mass, absolute value. So just the magnitude minus the dimensions there. Okay. So with that construction, the claim is that this gives us the square root of alpha. Square root of alpha, aka it's the amplitude of the fine structure constant. That's one of the reasons why a lot of times you square the things. Wait a second. I said that wrong. I need somebody smarter than me. I just need somebody to correct me. Did I say the amplitude? Okay, somebody double check that for me. Um, but that's the claim, is because once you square this, and we get alpha. Now, there is disagreement with some newer experiments. Okay, now because one of the things too, it's great. Kurt actually said this really well, at least pausing, because Chat GPT, a lot of these AIs, you could say a lot of things, and a lot of times it wants to make you happy. It doesn't want to like lie usually directly, but here's the thing: you can use it to find interesting things that you didn't necessarily know about. And I'm not saying that it can't do things. It seems to have done amazing things past different high level exams and all this stuff. Um, there does seem to be a limit on the entropy of natural language is a very interesting thing going around. You can check it out from Welsh Labs. They have a great thing on the amount of like compute, the data set, and basically it really just seems like physics there. I guess that's why a lot of physicists were on the paper. But as they were going through it, they found basically there does seem to be a bit of a limit. It's kind of also follows a logarithmic curve of some point, but again, that's feel free. That's Welsh Labs. They do a lot of stuff on LLMs and stuff. But the thing is, with that, the whole point of my 40-second ramble was Kurt was saying, yes, you can find things that'll show you interesting things. All right, well, this obviously has to be the answer. Now, were you prompting it looking for something? Was it you were intuiting that you could find it and get it to say a whole bunch of words and okay, we finally see? Because I've done that. I've totally done that. Now, how much time do we spend trying to falsify things? It's not like we'd ever be like, la, 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 la. I mean, nobody would ever do that on the internet. It would be childish. Childish. Oh God, it sounds horrific. All right, well maybe not as horrific as burning in the back of some children's toys recently, but that's just the story for another community. Um, God, it's a very interesting world in which we live, ain't it? Now, the whole thing with this is, and I brought that up, is because okay, if there are measurements, and it seems to depend on how you do it. Why do we get certain measurements? Why does the Berkeley measurement show very good agreement with like 1.02 sigma or 0.03 sigma with this construction, but the other constructions, for those that have no idea what the heck we're talking about, fine structure constant alpha, it's ends up being. Let me just look this up. Basically, the once you get past the, it's 0 point. Oh, am I trying to think of it which way? The inverse way. It's like 0.72 to not 25999. Hold on. Let's do this. Fine. God, the amount of anyone else get that? It's like I'm trying to remember. I could just look it up much more quickly. All right, so let's share our screen again. All right, code added value fine structure. Okay. So here's the claim, and this is to -3, so we should have a 0.007297352. Now, I would claim I have a difference of opinion, thinking that this should be like a 7 and then 2. Now, before I think this most recent update, the error bars were like much larger. They were quite a bit larger. So right now, defined structure constant, the thingy that got me here to the Physics Monastery, it's actually one of our biggest sigma differences. Full disclosure, 7.5 sigma. How do I explain that? Well, the short, and we'll get into some of the detail, also alpha's technically defined by this elementary charge squared divided by 4 pi, the electric constant, h bar times the speed of light. You can reduce that to simply the elementary charge over Planck charge, you square the whole thing. Why? Because that's what it is. Because when you actually go to that and you take the square root of that, you end up realizing it's the Planck charge. Because we have elementary charge, and Planck charge, and then we square the whole thing. Oh, I don't know. That looks basically like what we were just looking at, right? Cool. All right. So that's what we got there. Okay. So the update is we also got oh, hey, Kelly Shaw. Jax, good to see you. Rick. Uh, oh. I feel like I heard somebody say that, Rick. People say lots of things on the internet. And I'm sure nobody else would ever just say lots of things that would not be true in real life either. So, all right, let me go back to the other thing. All right. So I'm like, all right, gotta entertain the idea. What if this was wrong? What if it's wrong and we'd want to be more right? So if there isn't a good reason why some of those experiments, and hear there's something where if you're taking a sum total of charge, that's one thing, but as soon as you have other dimensional components interact, that seems, I'm not an experimentalist, so I'm just like, that's what I kind of the gist that I wanted to hear, because that might explain it. And if not, I'm like, all right, how could we rectify this? Well, is there something we could modify this by that we could still tell a story that would maybe make sense. Well, we looked. You could do log, oops, sorry, log 2 of the absolute value of the Planck mass. That gets us well into the current error bars and everything. And maybe you're not a big fan of logs. Maybe logs aren't useful. I would beg differ. But if you're not a big fan of logs, well, you get rid of that pesky log there. Okay. How could we adjust this? Well, you could divide the whole thing by root 2. I don't know. I don't know. Some people like root 2. Legend has this Hippothys of Metapontum died for root 2. He was allegedly like thrown off a boat by maybe the Pythagoreans because it was irrational. They couldn't take it. I'm, I'm sure nobody, there's not that way in the modern times where people would do something horrible or try to end somebody's career or even worse just because they happen to disagree with them. That would be childish. Now, side rant aside there. Okay. Is root 2 something that's useful in physics? Hey, I ain't a professionally trained scientist, but at least a lot of papers I've gone through, it seems to be important. Probably. Probabilistically, both. Is that a nan statement? I'm not a computer scientist. But okay, that was one of the updates because anything that we're going through, it's like, all right, what if it's wrong? Okay, you got a red team and be able to like, okay, well, if this wasn't the case, was this the case? What makes sense? Does it actually grok, so to speak? And then they follow where the evidence goes. Because if you're doing something, it's like, all right, this is great, this is great. And it's like, well, we seem to keep on. Yeah, it seems to be going out there. It seems to be going out there. It's like, we just listen. We do something and it doesn't work. We can keep doing it. Maybe it will work. Depending on who you ask, statistically, given enough iterations of reality, it might happen. Now, is that the best way to dedicate our time, resources, and efforts to help move humanity forward? I ain't a politician anymore. I served a single term in the College of Management representing the computer division because everyone else seemed to already live on campus. I'm just saying people that have a voice. That's all. Um, what else have we got going on? That's around, I don't know, 137. Collective variables that go into these equations. X is saying, like the vertices in a higher dimensional symmetric object, different facets, same underlying reality. Okay. Speaking of weird voodoo-like shapes, oh, I think we might be back. There we go. All right, it's all right. Yes, the moment the most number of people are tuned in, we have to cut the fade because we're live. And that's what you do on the internet. It's all right. Let's go through here. We have Wolfram. Yes, the Wolfram. Oh, already being recommended. Not this one. We'll bring it up. Let's present. Yes, screen. Wolfram Institute. Boom. Okay. So, like, listen, live science. If you don't already have it prepared, it can be. That's the tastiest thing here that I've seen. Qubits from Qubit, I think. No, it was the hot vibration one. Okay. For for those of you just joining us, this is from a recent Wolfram Institute. Shout out to my friends at the Institute. Uh live stream that they did about was from our friend Nick Merzan, a long time Wolfram person, as far as I know. Um, Very nice person. And what they're looking at here, if we look through,
This is regular convex
a
equations. And just show
they're
this.
looking at the 600 cell because apparently the 600 cell, and again, they're just
And
browsing
then
for Wikipedia,
we
just trying to
put
get a
on
feel,
128
first
cells
level
according to our
approximation
code.
for what's going on. So the 600 cell happened to be the particular geometric object that Nick, oh, that was the 120 cell. Okay. Um, Basically, the 600 cell, for those who don't know, is a four-dimensional platonic solid, aka a hypericosahedron. I did not know until like the past year or so that there were four-dimensional platonic solids. That's a crazy thing, but apparently within his structure, what he was trying to do is he was trying to model qubits. And qubits, a lot of times, it's, well, apparently you use root 3. Why? Because that's a qubit type thing. I don't know. For the purposes of this, I'm just highlighting that basically he was utilizing quantum potato chips, as he called them. He also has a paper out. Basically, he was going through and he was modifying things and utilizing tetrahedron to basically map things out and go through different transformations. So
He
now he's
just
trying to
give you
model the hot
like a
vibration
longitudinal
here.
attitude. So basically point on a sphere, and the third angle is like a circle emanating from it. That's the
There all the
final.
stuff in there,
That's
and
why
then
it's
he's
called
got
Hall
some
vibration.
really cool ways.
Or maybe it's like a
And basically, he's
long
modeling
history.
these as like
Somebody that
surfaces, and
first time
basically
written
surfaces
like this
taking
kind of
particular action.
surfaces.
And that looks
This
a
is
lot like a
essentially just
Mobius
pick
strip
one
to
of the
me.
angles from those
Ugh.
three and try
I
to
I just found it
map third
fascinating when
angle
I heard it.
at
I was
two angles
literally
from
laying
surface.
down when they were doing
Then
it. I
just
was just
rotate one
listening.
of the angles.
And all of a sudden,
Like
I heard
so one of the
something. I'm
angles is
like,
just
he was
like a
showing an
point.
image. Then I just like
That's
lift
how
my
you
phone
can
up and I saw, I'm like, wait a second. Does
span
that
the
say
ball
600
any
cell?
point in the ball.
Is this
Like
a hot? This
Right.
this is the same presentation
you
with the
can do it
hot
in three
vibration.
different ways.
You
It's
have
a
my
ball
attention.
boring one.
Okay. So why am I bringing up a random tale? Okay, of course I have to relate it back because there was a calculation. This is still the craziest calculation I have ever done. I'm still not sure what to make of it, but remember our little box friend over here. Okay. Now, I was looking for something about the derangements because, again, we're going to say all these things. So, like these different values, the total magnitude that we have, we're taking the magnitude, and this was at -44. So that'd be a magnitude of 44. Length would be magnitude of 35. Charge is 18. Mass as 8, and temperature is 32. If we take the absolute magnitudes of the exponents there, because we're claiming that these are derangements. There's only a certain way we can organize these different things. And the way we go about organizing these in a particular geometric fashion should lead to the stuff doing the things that we observe. Okay. Hey, when I just say it like that, I mean, duh, it should be just obvious, right? How does it happen? I don't know. But when you look at this thing is within all of our 288 constants on the poster. It seems to be a common thread. This happens when you put it in, basically, it comes out as the ampere constant. It listed as 10 to the -7. Again, we believe it's a little bit different, but for sake of argument, let's continue with this. All right. So that got me to thinking, what if I were to take these derangements, these mysterious derangements, don't know what they are, but we think they're important. And the model is basically, a lot of the model is based upon it. Again, if you can find a better closed form or something like that, and that's more accurate. But it makes our job easier. That's fine. Nobody has to use this. Feel free to use it if you want. Maybe it's useful. But we go into a little inversion boundary here. All right, so we have the Planck mass that has 8 derangements. All right, so we do 8. We have the Planck length, 35 derangements. 35. Due to standard algebra, we're going to multiply those guys together. And I'm going to divide it by qp squared. That's the Planck charge. Charge is 18. 18 squared. Okay. What does this come out to be? This comes out to be the the value of 70 over 81. I had no idea what that means. I get this number. I'm like, all right, what is this? But when you think about it, it's like, all right, that ends up going to whatever it is. This is blah, blah, blah. It ends up just being, you, you can reduce it in very interesting ways. So let's just do this rather than me trying to grind my head to do very basic arithmetic. This is why Professor Wolfram is far better at any of the stuff than I am. All right, so we go over here, boom. All right, boom, boom. All right. So what are we doing? We're doing, I know, how exciting. We're doing basic math. 8 times 35 divide by 18 squared. Yes, I know. What a fascinating result. 70 over 81. Again, means absolutely nothing. Unless it's a decimal approximation. Again, I don't know what this means. Maybe Wolfram Alpha might have a clue upon something that might be useful. 70 over 81, we saw that. Okay, the Wadsworth is basically just like a 0.3 factor. And then we got this. And that was the point I'm like, what the? Why do I say this? All right, that 35. All right, so 35. Wait a second. This is going to have something to do with like space or something, or length. Something to do with space. I don't know. Space, a structure. Maybe we're building something. Okay, so we had a 35. I can intuit that because that's one of the things that we put in. Okay. And then we get this. We get 6 times, what the heck is this? T sub 20 VE. That's the 20 vertex entropy constant. Where? What the heck is that? Okay, don't worry. Shouldn't. It was always something that I would see pop up in very interesting places. The first place it ever actually seemed to be an answer. And it gets all the digits because that is equivalent. The 70 over 81 is equivalent to that. Okay, what is the 20 vertex entropy constant? These math. Oh, math world works. Okay, I just need to bring it back over. Okay, boom. There we go. All right. So what is? Get in the wrong window. I'm a terrible host. Here we go. 20 vertex entropy. Okay. Let L denote the n by n triangular lattice with a wraparound. All right, so we got a triangular lattice. Okay, let's crawl them back around. Color orientation, L of assignments of a direction on L. The orientation, blah, 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 it ends up being this. Okay. So feel free to check that out. But when you go onto the OEIS, was that the online encyclopedia of integer sequences? Okay. It has some very interesting, because it was only recently named term coined here for the first time. So people have known about this, but it was named this. And why did they name it this? Okay. So equivalently, the area in the complex plane of the smallest complex set containing all order 6 roots of unity. Of unity. Well, it's not like the imaginary golden ratio has like 6 roots or anything. I mean, I has 4. Subtracting 2.5, i.e. dropping the first 2 digits, we attain blah, 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 9.8, which is the limiting mean cluster density for a bond percolation of probably 1/2. That seems like a very random thing. The constant is also the minimum radius of curvature of the exponential curve occurring at x equals negative log 2 divided by 2. Okay. Lemaitre proves that this is the critical impact parameter of a bare black hole in multiples of the Schwarzschild radius. That is, light from a distant source coming towards the black hole is captured by the black hole at smaller distances and deflected at larger distances. For any triangle ABC, sine A plus sine B plus sine C equals 3 times the square root of 3 over 2. Equality is attained only when the triangle is equilateral. Okay, well, that's basically our sequence right there, isn't it? I believe it is. 3 square root 3. All right. No? Okay, it's whatever it says it is right there. It's a very interesting thing. Okay, we go back to our friend here. Now, I swear, we're coming up on the 60-minute mark. We'll wrap it all the way back around. All right. We get this thingy here. Now, how the heck do I intuit this? All right. 620 vertices. Okay. 6 times 20 is 120. So I'm like, all right. Polyhedra with 120 vertices. Oh, we have our friend, the discus tricotahedron. The ferrous solid, that comes up. Okay. Now I may have slightly, okay. Basically, I originally went to the 120 cell because I'm like, oh, 120 cell. But when you look at it, it actually had 600 vertices. Curses! I was off. I was off. Unless we go to its dual. The 600 cell, which Nick apparently found extremely useful in his presentation, or at least it happened to work. 120 vertices. Okay. Now, because we got to go back, because we need to follow some train of logic, even if it's a crazy train, I claim. Okay. So we get 120 vertices, but it's squared. In our convention, if we square time, we're saying 2 hours of time there and everything. Okay. So how could I get 2 of those things? Well, it's not like you can't have one without the other. Yes. I'm making a married with children claim about the conjecture about the 600 cell and the 120 cell. What if the fabric of reality was us living in the dual existence between 2 4-dimensional platonic solids? I think that's worthy about getting thrown off a boat. I was never actually thrown off a boat. Violence is wrong. I was voted most likely to be thrown off the boat, though. Why? I was an annoying little kid. I also threw an Eskimo artifact off the side of a glacier because I wanted to see how far down it was. I'm passing around this old pewter cup, Ben family. I'm going to hell for so many reasons. But let's catch up a little bit. Yes, there's a lot of stuff going on. Yeah, 120 is it's also 5 factorial. So there's a lot of interesting stuff and things going on. But all right, I've been going on for an hour, and it's been fun. We got a few folks to join us. Maybe I'm going to try to do this on a bit more of a regular and frequent basis, probably earlier in the day. And we have some interesting folks that I'm aware of. If they have some interesting comments or questions, probably have some folks on. So just try to have a good time and try to move humanity forward best we can. So that's all we got right now. Take care of yourselves and peace out, everybody. Catch you on the flip side.